We're all familiar with the concept of black holes, those gravitational giants that consume everything in their path. But what if I told you that there exists a cosmic entity that defies the conventions of physics and challenges the boundaries of imagination? Imagine a region of space-time where matter and energy burst forth in a dazzling display of creation, rather than being swallowed into an eternal abyss. Consider the possibility of an entity that stands as the inverse of a black hole, a force that repels rather than devours, that ejects instead of engulfs. These things are even scarier than black holes. In this video, we are cracking the mysteries of white holes. We answer the unanswered questions like, what happens if a white hole and black hole collide? Join us on this voyage to dissect the secrets of these cosmic giants. In the vast expanse of the cosmos, where black holes swallow everything in their path, there exists an enigmatic and theoretical counterpart, a phenomenon that challenges our understanding of space, time, and the very nature of reality: white holes. Before we delve into the enigma of white holes, we must first understand their opposite, black holes. These cosmic giants arise from the remnants of massive stars, their gravitational pull so intense that not even light can escape them. But what if the story didn't end there? Enter white holes, hypothetical objects where matter and energy are seemingly expelled rather than devoured. White holes are a theoretical concept born from the equations of general relativity. While black holes pull everything into their depths, white holes are thought to repel matter and energy. However, their existence raises fundamental questions about the nature of time and the behavior of matter under extreme condition. The concept of white holes challenges our understanding of time itself. While black holes trap everything within their event horizons, white holes are theorized to expel matter and energy from an unknown origin. This potential reversal of time's arrow has sparked debates among physicists for decades. Like black holes, white holes have properties like mass, charge, and angular momentum. They attract matter like any other mass, but objects falling towards a white hole would never actually reach the white hole's event horizon. Imagine a gravitational field without a surface. Acceleration due to gravity is the greatest on the surface of any body. But since black holes lack a surface, acceleration due to gravity increases exponentially but never reaches a final value, as there is no considered surface in a singularity. In quantum mechanics, the black hole emits Hawking radiation, and so it can come to thermal equilibrium with a gas of radiation. Because a thermal equilibrium state is time reversal invariant, Stephen Hawking argued that the time reversal of a black hole in thermal equilibrium results in a white hole in thermal equilibrium. Consequently, this may imply that black holes and white holes are reciprocal in structure, wherein the Hawking radiation from an ordinary black hole is identified with a white hole's emission of energy and matter. Objects inside a white hole can leave and interact with the outside world, but since nothing can get in, the interior is cut off from the universe's past. No outside event will ever affect the inside. White holes emerge from the solutions of Einstein's theory of general relativity, devised by Carl Schwarzschild in 1916, just a year after the theory was first published. Schwarzschild was the guy who wrote down the mathematics that describes black holes in the universe as completely collapsed objects. He had to make a choice. There is nothing in general relativity that dictates which direction time flows in. You could point the clock in this particular direction, and that's what gives you this picture where things fall into a black hole. That's where gravity is attractive, but you could also choose the opposite direction in which time flows and get the opposite effect. So as well as a black hole, the mathematics of Schwarzschild also gives us a white hole by just flipping the way that time works. A white hole is almost like anti-gravity endlessly ejecting material. With a white hole, you have an event horizon, where stuff from the inside crosses the event horizon and gets ejected into the universe, and you can't actually get into the white hole. The theories surrounding white holes are very interesting. Let's take a look at them. Some theories suggest that white holes and black holes might be connected by traversable wormholes. These hypothetical shortcuts through space-time could potentially allow matter and energy to pass from a black hole to a white hole, or vice versa. Such a scenario raises questions about the stability of these connections and the potential for time travel-like effects. Other theory says that white holes might offer a solution to the black hole information paradox. This paradox arises from the apparent loss of information when matter falls into a black hole. Some physicists have suggested that white holes could be connected to black holes through wormholes, allowing the information that enters a black hole to be reborn in a white hole. Now let's think of an interesting scenario. What happens if a black hole and white hole collide with each other? When a black hole and a white hole collide, their opposing gravitational forces would generate a cosmic drama of unimaginable proportions. The black hole's intense gravitational pull, which engulfs all nearby matter and light, and the white hole's repulsive force, which expels matter and energy outward, would clash in a colossal cosmic showdown. As the two cosmic entities approach each other, the fabric of spacetime would be subjected to tremendous stress. Gravitational waves, ripples in spacetime itself, would propagate outward, carrying the news of this unprecedented collision across the universe. These waves would be generated in intricate patterns, reflecting the intricate interplay between the black hole's devouring nature and the white hole's explosive energy emission. Upon collision, the event horizons of the black hole and white hole would meet in a maelstrom of energies, creating an arena where the laws of physics as we know them might break down. The space-time curvature would become immensely complex, potentially giving rise to exotic structures like wormholes, hypothetical tunnels, through space-time that could connect distant parts of the universe. One of the most intriguing outcomes of this collision would be the potential for the reconciliation of certain paradoxes. Black holes are known for violating the conservation of information, as matter and information that fall into them seemingly disappear from the universe. In contrast, white holes expel matter and energy, seemingly creating new matter out of nothing. A collision could offer a resolution to these contradictions, allowing matter and information to flow between the two entities in a way that respects the laws of physics. Furthermore, the extreme energies released during this collision could lead to the creation of new particles and exotic forms of matter that defy our current understanding. The energies involved might provide a glimpse into the realm of quantum gravity, where the effects of both quantum mechanics and general relativity intertwine. In the wake of this cataclysmic event, the cosmos would be forever changed. Gravitational waves and radiation from the collision would travel across the universe, leaving traces that could be detected by advanced observatories. Humanity's understanding of the universe's fabric would deepen, and new avenues of research would open up, potentially leading to breakthroughs in our understanding of the most fundamental aspects of reality. While the collision of a white hole and a black hole is a fascinating idea that sparks the imagination, it's important to emphasize that our current understanding of physics and our knowledge of these hypothetical entities are limited. As such, the consequences of such an event remain firmly rooted in the realm of scientific speculation and exploration. But do white holes actually exist? The truth is, we've never seen one, and we don't expect to ever find one within our universe. Event horizons, unfortunately, are very good at hiding whatever else occurs on the other side of them. There may be something very interesting at the central locations inside each black hole in our universe, but we'll never be able to access them. There may have been something very interesting occurring in whatever birthed our universe before the onset of cosmic inflation and its aftermath. The hot Big Bang, but we have no way of obtaining any information about that time. It's worth keeping in mind that general relativity admits white holes as an equal possibility to black holes, but that only the observational evidence for black holes has been found within our universe. While mathematics can tell you the possibilities for what could occur, only observations, measurements, and experiments can tell you what does occur within the universe. White holes remain an intriguing possibility, but their existence, at this point in time, can only be said to be speculative at best. As we conclude our journey through the captivating world of white holes, we invite you to continue your exploration of the cosmos with us. If the mysteries of the universe have ignited your curiosity, be sure to hit the like button and subscribe to Astronovia. By staying connected, you'll be part of a community that's passionate about unraveling the secrets of the cosmos, one cosmic enigma at a time.